installment of RSA, the Shor's algorithm series. Our session 3 is RSA in quantum computing. So what we'll do here is we are going to discuss the theoretical basis of Shor's algorithm. Okay, so you cannot see any programming here. It's mostly mathematics, but that's a good thing because at least you will have a more solid foundation when it comes to Shor's algorithm. Okay, so we will have to have some review first. So in Shor's algorithm, so in RSA, we have a message A, and then we want to encrypt it. So using a number C, okay, and we actually have two numbers here, which is the which compose the public key. So N and C. Okay. Now N is a product of the two prime numbers P and Q. Okay. So this P and Q, we don't reveal this. Okay, to the world. No? This is something which is it's actually very hard to factor it. Okay, so given N, N has only two factors, P and Q, but it's very hard to factor it P and Q. And that's the basis of RSA, the hardness of the problem of factoring N. So given N and C, if you have a message encoded as A, as number A, then what you can do is raise this A to the power C and get the remainder. Okay, so get the modulo, the remainder when you divide it by N. And that remainder is equal to B, which is called a cipher text. Okay, so it's already the image. Okay, now so I mentioned about the public key C and N. There's also a private key. Okay, so the private key is the one that is kept by the person who can decrypt the message. Okay, so for example, if we have Alice and Bob, and Bob wants to send a message to Alice, given the public key of Alice, which is N and C. So if Bob sends the result, which is B, only Alice can decrypt that using her private key. So what she can do is just raise the raise the ciphertext B to the public key power, and then get the remainder, and then that will give her the plain text, which is A. Okay, so we assume that Alice is guarding the private key very well, that no one can get it from her. Okay, so what does a cracker do? Okay, what does someone who wants to crack it have to do if he or she, or let's just say she, because in the usual characters in security are Alice, Bob, and Eve. So Eve is Eve's dropper. Okay, so yeah, Eve. Yeah, so what Eve will do is to find a number called the period, okay, represented by R. So R is defined to be that number which, when you raise B, okay, so B here is the ciphertext, okay, if you raise this, okay, to the power R and get the remainder modulo N, the remainder is 1. So once you get that, then it's already very easy to decrypt. this ciphertext. We will show that in the next slide. Okay. So once we know R, what we can do is compute the inverse of C. Okay, so remember that C here is your number that allows you to encode that you use to encode the plain text. And so given R, so this is the one that you discover, right? So once you get this, what you can do is solve this equation, okay, for D. Okay, so solve this equation for D. So by definition, CD prime is equal to 1 modulo R. It means that there is a number S. Okay, we don't care what S is as long as S exists. Okay, such that S times the base here, or this one here is S times R plus 1 will give you the C times D. Okay, so that's when you find D here is your unknown. Okay, so you solve for D. It's very easy to solve this, and it's actually very the algorithm is very efficient. Okay, it's called the Euclidean algorithm, so you can solve for that. And so once you get the inverse, what you do is given the ciphertext, you just raise it to the power D prime modulo n, and whatever is the remainder is your original text. Okay, it's your plain text. So that's how to crack the RSA. Okay, but how do you actually compute for R? Okay, so that's the okay. So in here is this slide actually shows us why it works. Okay, why it works. So it works because we know that B is equal to A to the C. Okay, now so A to the C raised to the D prime is CD prime, right? So CD prime, but we know that CD prime is equal to SR plus 1. Okay, so it's like this, and we know that the plus 1 here is just A to the SR times A. Okay, law of exponents. Okay, so but we know that A to the R, what is A to the R? A to the R is 1. Okay, by definition, the period. So which means that this entire quantity here equals 1, which leaves you A. Okay, so that's the mathematics of the period finding. Okay, so we are just we actually tackled this in the previous lecture, but this is just a review. Okay. So okay, so what is Shor's algorithm? Okay, what does it compute now? So so we know that a quantum computer can allow us to do superposition, and because of superposition, we can actually generate all numbers. For example, if you have 3 qubits, then you can generate, by superposition, you can generate all numbers between 0 to 7. Okay, so if you have so which means if n is equal to 3, okay, so if n is equal to 3, let's just say if n is equal to 3, then 3 qubits. Okay, so which means that we can generate all numbers from 0 to 2 to the n minus 1. Okay, so for example, we can generate 0, 1 until 7. Okay, because 2 to the 3 is 8. So So there are 8 of these numbers. Okay, so it means that if you have n qubits, so you can generate 2 to the n minus 1. And the thing about this is that if you apply an operation, like for example, b to the x modulo n, okay, if you apply an operation to that qubit, to those qubits, okay, you actually apply it to all numbers, okay, between 0 and 2 to the n minus 1, okay. You are actually applying b to the x modulo n, where x here stands for your number, okay. So this is one of the numbers generated by the superposition, okay. And so we know that when f of x is equal to 1, which means this means that we have found our period. No, our period is the exponent which allows us to get an answer of 1. Okay, so that's the reason why we do this. No, so if you were patient enough, okay, if you are patient enough and you have infinite life, no, it means you cannot die, then you can actually crack the RSA encryption if you live up to 300 trillion years, no? Just by writing a for loop. And when you do a for loop, so for every number that you generate, okay, from 0 to 2 to the 2048 example, whatever that number is, so you generate all numbers and apply b to the x. Okay, so for example, b is your encrypted text. So you do a for loop to get the value of f of x for all x between 0 and this number. And then what you do is the moment you find the answer equal to 1, then you get your period. Okay, the period is just the value of x that makes it 1. Okay, however, since we don't have a infinite life, we have to resort to quantum computing. Okay, so how do we set it up? Okay, to set it up, we need to prepare 2 registers. Okay, so the register is the input and output register. The input register will generate all of our numbers, okay, all of our x. The input register will generate all of the x here, okay. So the input register will generate all of the x. And the output register will generate all of the b to the x modulo n, okay. So and then we have so how do we do that? How do we actually do this? What's the operator? Okay, there's a term called operator. Okay? So it's the unitary operator that actually computes for this b to the x mod n. Okay, so this is represented by u of f. Okay, so u of f, u sub f, applied to the input and output register, which is x and y, okay, it will give a result, which is the value of x, which is not what you call this, it's not modified, but what is modified is the output register, okay. So the output register is just whatever is the value of y here, you get the XOR with the value of f of x, okay, where f of x is the modulo function. Okay, so this kind of computing setup is also known as reversible computing. Okay. Now, so superposition. How do we generate all possible values of x? We do this by applying the Hadamard gate. Okay, so if you are not familiar now, let's do a review of Hadamard now. The Hadamard gate is like this. Let's get some other color. Hadamard is represented by H. Okay, and if you operate it with 0, it will give you what will give you 0 plus 1 over the square root of 2. Okay, if you operate it with 1, the qubit with the value 1, state 1, then it will give you 0 minus 1 over the square root of 2. Okay, now what happens if you have 2 qubits? Okay, so if you have 2 qubits, this is how you do it. Okay, you just so this is just notation. Okay, so this will just become this is called a tensor symbol. Okay, so you have 2 qubits now. That is just equal to H acting on each qubit separately. Okay, so HH. There's actually a tensor sign here in between. So there's a tensor sign in between. Dito. Oh, sorry. What happened here? Yeah, so there's a tensor sign. Okay. There's a tensor sign, the letter X. Okay. So if you perform the operation, what will happen is that you'll get this one. Okay, sorry, you'll get this one. You get H0 tensor H0. This will give you 0 plus 1 over square root of 2 multiplied by 0 plus 1 over square root of 2. Okay, so which means that if you expand this, okay, so if you expand this here, you will get something like 0. Oh, sorry, you get something like 0 0 plus 0 1 plus 1 0 plus 1 1 over 2. Okay, because square root of 2 times square root of 2 is equal to 2. Okay, so what do you see? What you see is nothing but a superposition. Okay, so summation of x equals 0 to 2 to the 2 minus 1. Okay, and then x here. Okay. So what I'm just giving you is the superposition for 2 qubits. But for general qubit, this is what you get. Okay, for general qubit, this is what you get. This one here. This is what you get. Okay, so that's the action of the Hadamard. Okay, now, so now that we have a superposition of numbers in our, because of the Hadamard, our input register is now in superposition. Okay, so that becomes our input to the unitary operation here. Okay, which computes the modular exponentiation. Okay, so that's what happens. Okay, so the Hadamard here will give you this summation, and then what you do is because of you can, because of linearity. Okay, the linearity of operation, which means you can apply the apply the operator to each what you call that, to in addition you have a sum, right? But the one that you add, okay, the one that you add, so you can apply it to this one here. So which means that but this one is nothing but this one here, okay? So which means that but f of x is nothing but this modulo operation, okay, modular exponentiation. So once you apply once you apply the unitary operation on a superposition, you get this, okay? So what does this mean? What does this equation mean? It means that you have now computed every possible value of b to the x modulo n, okay? You have computed all possible values for all x generated by the input register, okay? Now it's just a matter of finding which one of those is equal to 1, okay? And then you get the period. But that is not actually what Shor's algorithm does, because the thing is, when you measure, so imagine you now have two registers, okay? So I mean, not imagine, but you have to realize that you have two registers, okay? This is the first register, and this is the second register, okay? What you will do, the next thing that you will do now is to measure the output register, okay? So what happens if you measure the output register? It will collapse into one of the numbers, okay? Okay. So it will collapse into one of the numbers, okay? So let me give you an example of like let me give you an example of this one, okay? So this one here, let me give you an example of how it looks like, okay? Okay. So it's like this. So this I'm now in my Python, okay? So because I don't have a quantum computer here, I will just be able to do a for loop, okay? So for I in range, all numbers between 0 and 16, okay? So what I want to do is compute the power or the modular exponentiation, okay? Power of, let us say we have a number 13, which is our ciphertext, okay? So 13 raised to the I modulo 15, okay? Where 15 is our n. So what will happen is it will do something like this, okay? So take a look. So the answer is 1, 13, 4, 7, and then 1, 13, 4, 7. So you see a pattern, right? So you see a pattern that so for example, like that, it repeats every 4. In other words, the pattern is the R, which is the period, is actually 4, because every time you do a count 4, the next number becomes repeats. No, so for example, 1, 2, 3, 4, and then it repeats again. 1, 2, 3, 4. It repeats. So the period here is 4. Okay. Now this one here that you see 1, 13, 4, 7, 1, 13, 4, 7. That is the value. That is what becomes of your output register. Okay, so your output register is actually a superposition of all these numbers. Okay, but you see that these numbers are nothing but repeated, diba? So it's repeated. So which means that there are actually only 4 numbers now in superposition. Okay, and so what happens if you measure the output register? It will give you either a 1, a 13, a 4, or a 7. Okay, so if you measure the output register, it will give you a 1, a 13, a 4, or a 7. Okay, Now, if it gives you a 13, what will happen to the input register? Okay, so this one is the output register. Okay, now if you measure the output register, you can get a number. Okay, and what number you can get can either be 1, 13, 4, or 7. No? It doesn't matter. The thing is, there are only 4 numbers. The next thing you'll do is to measure it. Okay, so okay, sorry, I was ahead of myself now. This is just the definition. We still have to apply it, no? we still have to apply it to the value of x. Okay, so what's x? So we apply it to here. This one here, no? So this one is your superposition. Okay, so you apply the quantum Fourier transform, and by linearity, you can apply it to each element of the sum, no? Each element of the superposition. So that's why we are able to put this inside the summation. Okay, that's the reason, because of linearity. And now that we have that, we can now focus on this one, which is applying this to the value x0 plus kr. Okay, now let us go back. Okay, let's go back here and let's take a look. Okay, so the quantum Fourier transform will give you this now. So it will give you x times y. Okay, where y is the value of this one here, the value of your qubit now. Okay, so let's go back to the next slide. What is y? Okay, so y is still y, but x is now so now this becomes x times y. Okay, so what you have here is this one, okay, multiplied by y. Now by law of exponent, you can just you can actually so by law of exponent, you can actually turn this into these 2 factors. Okay, which is the first factor here. This one here is due to this one. Okay, and this one here, and this one here is due to e to the 2 pi I multiplied by kr y. Okay, so now you have separated it. Okay, but okay, so if you take a look at the summation, you can invert the summation. Okay, so sorry, it's not really invert, but you can rearrange the summation. Okay, so what you can do here is this summation that you see here in the outside, which is k from k equals 0 to m, you can actually put this inside. Okay, so you can reverse the order. Okay, and since this one is the summation here is from the index of summation is k, since this factor here doesn't have k anywhere in it, you can also factor it out. Okay, so that's why it's here outside. Okay, now, so what you can see now is that this is nothing but a summation or a superposition of all values of y, okay, from 0 to 2 to the n minus 1, And this one here that you see, which is which I encircle in red, okay, this is nothing but the probability of that y, this value of y, to be to occur when you measure this superposition. All right. So when you measure this superposition, you will get a y. Okay, you will get a y. But what is the value of y? No. So the value of y, the one that will occur most frequently, is related to the probability of it occurring. Okay, which is the probability amplitude. Now, at this point, we are already so this is like the second part of the Shor's algorithm. We measure after applying the what you call this, the Fourier transform to the input register. We measure it. Okay, so when you apply the Fourier transform to the input register, it will give you a superposition of all of these y's. Okay, and then you measure it. Okay, so when you measure it, it will give you a number, okay, which is equal to y. No? And we want to know what is the and that number will occur depending on the probability, which is the one here encircled. Okay. So before I get ahead myself, so if you make a measurement on the previous equation, on the state, the probability of getting a specific value of y is equal to the square of the modulus. No? So in other words, you square this. Okay, you square this. Okay. So if you square that, this is what you'll get. Okay. Now, by the way, if you this factor here, okay. Sorry. Okay, what happened? Okay, so this factor here, if you I always forget. So that factor there, when I say square of the modulus, what do I mean? Huh? Why? What I mean is that let's do this, okay, so that you'll understand. So what's the square of this one? What's the square of this one? How do I put this here? Okay, sorry. What is the square of this one in blue? Okay, let's do this. Okay, e to the 2 pi I x0 y over 2 to the n. Okay, so when I say square of the modulus, what do I say? What do I mean? It means that I multiply it with its complex conjugate. Okay, so what's the complex conjugate of this thing? The complex conjugate of this thing is e to the negative 2 pi I x0 y over 2 to the n. Okay, so by law of exponents, this is just equal to this quantity, this thing, minus this thing, is equal to e to the 0 is equal to 1. Okay, that's why it disappeared. Okay, it disappeared here. And then what will happen to this one here? What will happen to this one? Okay, what will happen to this one? Okay, this one will become 1 over 2 to the n times m. Okay, so that's what happened to this one. Now the third part, what happens to this one here? Okay, that's the thing which I want you to do. Well, you just have to show that this one here is actually equal to this one. Okay, so there's an exercise I'm going to send you after this after this lecture, so that you will, just compute it. That's what you call this simplify. Okay, you just use this formulas here, and then do this, and then you'll get this. Okay, you'll get this. Okay, so granting, let's have faith that that's the correct one. So what will happen is that the probability is therefore equal to this one here multiplied by this one here. Okay, so this is equal to this one. Okay. The probability of getting a y is equal to this quantity 1/2 to the m times n, and this sine squared. Okay. Now, if you plot this function, okay, what happens is that, and if we, for example, we let, okay, this letter f here, okay, this letter f, we define it to be this one. Okay, we define it to be this one here. Okay, because it's a very complex formula. Okay, so we just have to make it simple by calling it to be f. Okay, so if we do that, if we plot this, we actually get this one here. Okay, so you looking at this graph, okay, what can we say about this probability? Okay, what can we say? Okay, so we can say that at integer values, these are integer values. At integer values, the probability is high. Okay, there's a high probability that you will get these values here. But these values here are the values of f. Okay, so these are the values of f. But we are not looking for f. Okay, we are looking for r. Okay, so what is f? F is this one here. Okay, so we know that when we measure the system, you know p over q, but you don't know x. But you can approximate x by doing a continued fraction expansion. Okay, which I will explain later what it is. Okay, so given this theorem, let's apply that to our case here. Okay, so in fact we can find a y that is within 1/2 of the 2 to the values now. So we have a so if we go back here to, so we know that y is approximately equal to this one here now. So y is approximately equal. And if you take a look at this one here, these are the y's now. So these are the y's. Okay. Now, so since y is very close to this number, then we can say that y minus j 2 to the And what happens to this? This becomes y over 2 to the n, and this becomes this one here cancels, no? This one cancels with this one. Okay, so that's why we're left with j over r. Okay. Now, so this is our equation now. Now, if we let q be equal to 2 to the n, we are going to what we're doing here is since this is true, we can probably make use of the theorem that we discussed above. But if we make use of that theorem, then we will have to determine which is p and which is q. Okay, so if you let q equal to 2 to the n, then what happens is that this one equals our p equals y, q equals 2 to the n. Okay, so p equals y, q equals 2 to the n, and this becomes 1 over 2 q. Okay, so this one here is equal to 1 over 2 times q. Okay, because 1 over 2 times q is 2 to the n. Okay, so this is equal to 1 over 2 to the n plus 1. Okay, which is this one. Okay, so which means since that's the case, we can actually do partial fraction expansion to compute for r. Okay, so there is an exercise here. The exercise here it will show you that if you increase the number of qubits, okay, if you increase the number of qubits of the input register to be equal to 2 times n0, okay, where n0 is the number of qubits of your, for example, if you have a 2048 encryption, that's your n0. So if you multiply that by 2, it will give you 4090 4 times 2, 1024. Sorry, 2048 times 2, 4096. So if we have this number of qubits in our input register, then the estimated error of our of this one here, the estimated error of this one is less than, okay, so this what you call this absolute value, the difference between them is less than 1 over 2 to the 1 over 2 n squared. No, so now since n is a very, very big number and you multiply it by itself to make it square, and then you invert it, so if you compute 1 over 2 to the n squared, it's very, very small, so the error is so small, okay, which makes your estimate better. No, so we can therefore expand but because of the theorem, we can therefore expand y over 2 to the n via continued fraction expansion. Okay, so let's go back here. We can expand this to be via continued fraction expansion, and then continue until the denominator r is less than n. No, so because continued fraction expansion is actually is an infinite what you call this infinite series. You have to stop somewhere, and you stop when the denominator r is less than n. Okay, and then whatever r you will get, you will how do you know that it's a period? So you will know that it's a period if you get your ciphertext B and raise it to the r and get the remainder, and get the remainder when you divide it by n. And if the remainder is 1, then you know that you have the your r is a period. Okay, so once you know that it's a period, it's just a matter of doing this thing. Okay, it's just a matter of computing the inverse of C with respect to R, and then once you get the inverse, you do this. You raise b to the power d prime, and you get your original text. Okay, so how do we do continual fraction expansion? Okay, so we're going to do that here. So we have example here. Our parameter is n is 3127, and our C is equal to 7. Okay, so if our message is 1907, we can encrypt this using 1907 raised to the 7 modulo 3127 to give you 794. Okay, so that's the this one here we are encrypting. Okay, so this is our plain text and this is our ciphertext. Okay, now suppose we use Shor's algorithm. Okay, we use Shor's algorithm to compute. We use Shor's algorithm, and then we put the input register in. We applied the quantum Fourier transform on the input register, and then we measured it. Okay, and the y that we measured is equal to this one here. Okay, suppose that's the y that we get. Okay, so and suppose n is equal to 12. No, so ibig sabihin, what I mean is that 2 to the n is equal to 2 to the 12. Okay, so we are supposed to compute this y over 2 to the n. Okay, we're supposed to compute this using partial fraction expansion. No? So so since y is 14 for this one here, and then 2 to the n like that, this is the partial fraction decomposition. Okay, so let me just show you how it works. Okay, so 1446311. Okay, so let's say y, sabihin natin 1446311. Okay, and then the other one is sorry, I just have to, I cannot copy this actually. So 167772216. 167772216. Okay. So how do you do partial fraction expansion? This is how you do it. Okay. Take a look at this one here. Okay. This one is just equal to 1 over the reciprocal, no? So 167772216 over 1446311. Okay. So how do we do that? How do we so this is we do this copy. Okay. Okay, sorry. I think I must have got it wrong. 1677216 divided by, I don't know what happened to me. This 1446311. Where did I get this to? 1446311. Okay. So that will give you 11. Okay. So this will give you, this will then become 1 over 11 plus, what's the remainder? The remainder is this one here. Okay, 867795. Okay, so this becomes 867795 over 1446311. Okay, what's the next step? The next step is you also get the reciprocal of this, no? So this the next step is this becomes 1 over 11 plus 1 over 1446311 over 867795. Okay, so the next step is this one here divided by this one here. Okay, so that will give 1. The answer is 1. And then what's the remainder? The remainder is, okay, something like that, no? Now, so if you continue this process, so, and then you will have to stop somewhere. So once the, so in here, I stop until this one, no? Okay, I stop until that one. Now, if I convert this back into a number, a fraction, I get 5 over 58. No? So how did I do that? No? So let's take a look. No? So object eraser. Okay. Okay. Yeah. Okay. How do I do that now? So if you take a look at that, one here, this one here is actually 1 plus 1 over 1. Huh? This is actually equal to 2. Okay. And then this one here, so 1 plus 1 over 2 is 3 over 2. Okay. And then this one here is, what's next? This one. Okay. This one here is 1 plus 1 over 3 over 2, or 1 plus 2 over 3, no, which is 5 over 3. Okay. And then this one here will give you, this will give you, this will give you 11 plus 1 over 5 over 3, no? Which is equal to 11 plus 3 over 5, no? Which is equal to 55 plus 3 over 5, no? Which is equal to 58 over 5, no? But since this one is a reciprocal, 1 over 58, 1 over 58 over 5 is equal to 5 over 58. No? Okay, 5 over 58. So that's the value. But as you can see, 58, 5 over 58 is approximately equal to J over R, no? Okay, do you still remember that Y over 2 to the N is approximately equal to J over R? Okay, where do we get that? This one here, okay? This one here, okay? So we computed this one, diba? So once we compute this one, we know that it's approximately equal to J over R. So which means that R is equal to 58, no? But we don't know if that's a true R, no? We have to first check if it's a R, if it's a true period. And how do we do that? How do we do that? Is by substituting it with our problem. No? We have B is equal to 794. So you raise it to the power 58 modulo 3127, and it gives you 1. So which means that R is equal to 58. No? It's a true period. Okay. So because it's a true period, we can then compute for the inverse. No. The inverse modulo, the inverse of C modulo R, no? So we compute for D prime. Now, according to this, d prime is equal to 25. Okay. So now that we have d prime, we can then use d prime or 25 to decrypt our message, no? So our message is 794. Okay, raised to the 25
Yes.
modulo 3127, no? Which is our original message. Okay. Okay. So let's do that here. So power of 794 raised to the 25 modulo 3127. Okay, 1907. So if you oh guys, sorry. Have I always been showing this one? Burns? Hello? Are you still able to hear me? Did you see this, Asher, did you see this? Did you see me doing this? Asher, can you hear me? Did you see me writing this one? Oh, yeah. So I hope that you were able to see it. Yeah. So this one here, the 1907 here, we actually got that here. Okay. So when we initially, this is our initial text. Okay. And we got 794. Okay. And then what we do is we computed the period. And then once we got the period, we computed the inverse modulo. And then after inverse modulo, we computed we decrypted the ciphertext, no? And then we got A, which is our original message. Okay. Okay. Now, so that's the Shor's algorithm, no? So let's now, before we end, let's compute the probability of success, no? So the reason why we want to do we to compute for the probability is because we want to know because quantum computing is probabilistic, right? So it's not it's when you apply the Shor's algorithm, it's possible that you actually don't get the period. Okay, so the question is, how many times do I apply the Shor's algorithm before I get the period? Okay, so that's why you need to compute for the probability of success, the probability that actually get the period. Okay, so in order to do that, we want to evaluate probability of getting the value yj, where yj is this thing here plus some very small value. Okay, so where delta j is the distance of the closest y to the to this value here, no? So if we do that, we just have to plug this into our probability formula. Okay, so since f is equal to this one here, then this formula is becomes this one here. So we just put f back. Okay, and now after doing that, we then plug in the value of y, which is this one here. No? Okay, this is the one that we want to compute the probability of this one occurring. Okay, so because this one is a sine function, so if you you multiply the terms, okay, in the first in the numerator, it will give, and the denominator, it will give you this one and this one, okay. Now, according to the sign identity, the trigonometric identity for sine, which is the addition formulas, no? If you still remember your trigonometry, so we have this addition formulas, sine A plus minus B. So it will give you down here, okay? So the sign of a multiple of pi, okay, the sign of multiple of pi, multiple of pi is if this is your sign, okay, 0. Sine is 0, and this is pi over 2, and this is pi. Okay, if it's multiple of pi is equal to 0, so that's why I left with this one here. Okay, that's why you are left with this one, and the same goes for the denominator. Okay, you are left with that with these terms. Now, since sine for very small, as you can see, this 2 to the n is a very big number. Okay, for very small angles, sine is approximate. Sine of x is approximately equal to x. Okay, so for very small angle, sine of x is approximately equal to x. Okay, so which means the denominator here is just equal to whatever is in here, no? So this sine squared pi r delta j over 2 to the n is just can be approximated by pi r delta j over 2 to the n, okay, and squared, okay, because this one here is squared, okay. Now, what happens to the numerator? Okay, so since since 2 to the n is a very big number, and r is well, we can actually this one here, okay, this one here. Why is this true? Okay, you might be wondering, is that true? Well, let's take a look. Okay, let's go back a couple of slides. Okay, so remember this one here. A couple of slides. I think it was in the beginning. Okay, so according to this, m is approximately is equal to 2 to the n over r, or 2 to the n over r plus 1. Okay, so let's just say it's approximately equal to 2 to the n over r. Okay, so m is approximately equal to 2 to the m to 2 to the n over r, no? So n is approximately equal to 2 to the n over r, no? So which means that m times r over 2 to the n is approximately equal to 1, no? Okay, 1. So if that's the case, then what will happen is the numerator here. So we are going to find this m times r over 2 to the n. Okay, so this one here, m times r over 2 to the m is approximately equal to 1. So you'll be left with pi delta j, no? So pi delta j, which is this one here. Okay. Now, we are then going to determine what's the approximate value of pi of sine squared pi delta j, no? So pi delta j, we'll resort to graphing it, no? So this is the value. This is the graph of sine x, the one in red, and the the graph of 2x over pi, which is a line, no? A line segment between from 0 to pi over 2, okay, from 0 to pi over 2, we can see that this line segment here is always less than or equal to sine x, okay? So if that's the case, then we can approximate sine x to be we can approximate sine x to be sorry. So we can use this, no? We can use this. But what is x, no? X in our case is pi delta j. So what do you call this? 2x over pi is equal to 2. X is pi delta j, okay, over pi, okay. So what you have is you're left with 2 delta j, okay. Okay, so this becomes 2 delta j, and then you can just well, you can this one here, and then you can also cancel this, okay. So what you get 2m over pi, okay. So you get 2m over pi squared, okay. And then if you simplify this, you will actually get this one here, okay. This one here. So you know. So what happens is that it's actually independent of m, no? We don't really care what m is. So you cancel m, okay, and then okay. So what is m over 2 to the n, no? Okay, sorry, what did I do? So m over 2 to the n is 1 over r, no? So andito yan, m over 2 to the n. Okay. M over 2 to the n is 1 over r, no? So m over 2 to the n is approximately equal to 1 over r, no? So that's why we have this. That's why we have this. So the probability is approximately, it's this one is the lower bound, no? It's approximately equal to 1 over r times 1 over r times 4 over pi squared. Now, that's the probability of getting a specific y, no? So what is the probability of but there are actually how many of these numbers that we are we measure? If you go back to our for loop, this one here, if you go back to our for loop, and let's say that we what are the possible values of the so the possible values are, as you can see, this one is repeated, right? So 1, 13, 4, 7, 1, 13, 4, 7. So because the period the period r here is equal to 4, then the possible values of the output register are only 4. So there are only 4. So in other words, if you want to get the probability of success, the probability of getting a y, which is this one here, if you want to get the probability of success, so this one is the probability of getting a specific value, okay? But since there are r of those values, and you don't care which of those are, then the probability of success is actually R multiplied by 1 over R times 4 over pi squared. No? Sorry. Okay. So this is equal to cancel, 4 over pi squared. No? But what is 4 over pi squared? This is equal to 0.405. No? Okay, so by computing this, what did we get? No? Were we just wasting our time? No. So now we know that if we run the if you run the Shor's algorithm, there's a probability that we are going to get the answer of 0.405. Okay, so what does that mean? Okay,
Almost half.
So imagine you have a coin, diba? You have a coin, and then you have a heads and tails, diba? Now I have a question. What is how many times would you have to throw the coin in order to get ahead? No. In other words, my question is, what's the average number of throws that you will have to do to the coin in order to get ahead? Okay. Now the answer of that is this theorem here. The answer. So actually, the answer is 2. Okay, so you have to throw the coin twice, because by throwing it on the average twice, you get a head. No, but there's actually I mean, if you can see that, no, there's a that is in probability theory. So let V be an event that occurs in a trial with probability P. Mathematical expectation, or nothing, is also defined. Mathematical expectation is nothing but the average. No? The average number of trials, no, that you will have before the first occurrence of your V. Okay, before the, for example, before you get a head, is actually 1 over P, no? Because where P is your probability. Now we know that the probability of success for a balanced coin is 0.5, diba? So ibig sabihin, 1 over 0.05 is the 0.5 is the number of times that you are going to throw the coin. Now, if we apply this to Shor's algorithm, 0.405, 1 over 0.405 is the number of times we have to run on the average, run the Shor's algorithm before we can get a valid period. No? So for example, you run the Shor's algorithm once, you get a number, okay, and then you use partial fraction expansion to get the period, and then that period that you get, you have to determine if that's really a period, no? By taking your ciphertext, raising it to that number, modulo the n, and if it gives you a 1, then you're in luck, no? That's a period. So you can use that to decrypt your ciphertext. However, if it doesn't give you 1, then you have to try again, no? You try again the Shor's algorithm, okay? And then you get another number. Is that a period? No. Okay, and try again. So according to this, to our computation, you have to try on the average, no? It's not the maximum. On the average, about 2.4 or about 3 applications of the Shor's algorithm to be before you can get a valid period. So that's it. Okay. So any questions? I know it's only you, Burns, question, because Asher is he doesn't have a mic. Any questions?
Okay. Actually, it's really a question to myself whether I still have to go to all the before this session. I actually miss a lot. So I really have to go over the first topic to relate all this one. But a repetition is a principle of learning.
Tama yan.
So
yeah, that's true.
So that's the thing. So it has to be repeated.
But
I was just amazed na paano yung kasi the Fourier transform is something very important. And may Fourier transform din pala, no? Kasi I thought really that I did signal processing for a long time, like since like 2000.
Fourier transform is easy.
Oh, di ba? So I was surprised na really pwede pala yun. So
yeah.
So ganun pala, no? Kasi tapos ganun pa rin ang operation, no? Square it, and pareho actually. Yung talaga, you have to remember the qubits, but I think medyo talagang I really have to dig up a little more, lalo na yung mga naunang mga lessons, no? So
bro, the previous lessons, I summarize them into this 1, 2, 3.
Yeah.
3 pages. Yeah.
So I'm just getting ahead a little bit of myself. Kung halimbawa na all this, so this Shor's algorithm ultimately will land as a quantum circuit, I guess, right?
Yes. That's the good thing about this Burns, because the one that you see here, this one here. What is that? Where's the Fourier transform? So Shor's algorithm is actually the Fourier transform is the most important. Okay, so
okay.
Yeah, take a look. What's this? Where is the Fourier transform?
Nasa taas ata eh.
Nasa taas.
Nakita ko yung more.
Yeah, this one.
Yan.
Starting from that, you see that's mathematics, right? We can actually convert that into a circuit.
Okay.
Yeah. We can convert. We can decompose this.
I like that motivation.
Yeah.
Kasi kasi siyempre dati I remember solving the differential equation with operational amplifiers. So that's the most basic building block. No, analog computer naman yon, but okay. So yung Qiskit kaya niya yan?
Yeah. We're going to show you that. Yeah, we're going to derive it. We're going to derive the circuit, from the mathematics. That's a good thing.
That's good.
From the mathematics.
That's really a very good motivator, Kasi kailangan talaga madidikit niya to some reality or sort of, di ba? So yun ang tingin ko kasi yun nga, it's not entirely really it's really medyo may gray areas talaga na you have to accept it tapos transition ka doon sa circuit kasi the extreme is really just to get to the quantum mechanics part and never really get off from that di ba, from that to quantum ba. So